Welcome, everyone. Today, we're diving into object-oriented programming. I'm excited to take you through Chapter 1, which is all about introducing the OOP paradigm. On this first slide, you'll see the main title, and we'll start with a brief overview of what we'll cover in this presentation. We'll explore the fundamentals of OOP and why it's so important in modern software development. But for now, let's keep it short and get ready to learn. Let's start by exploring the introduction to the object-oriented programming paradigm. Here, we'll compare it to traditional structured or procedural programming. In procedural programming, the focus is on writing sequences of instructions that manipulate data, often through functions and procedures. While this approach works well for straightforward tasks, it can become complex and harder to maintain as programs grow in size and complexity. Object-oriented programming, or OOP, shifts the focus to objects. These are instances of classes that encapsulate data and behaviors together. This leads us to some fundamental concepts of OOP, starting with abstraction. Abstraction means simplifying complex reality by modeling classes that expose only necessary features, hiding the details that are not immediately relevant. Next is encapsulation, which involves bundling data and methods within a class, controlling how data is accessed and modified. This is closely related to information hiding, where internal details are hidden from outside interference, promoting a clear interface and reducing unexpected side effects. These concepts contribute to program reusability, allowing us to create modular components that can be reused across different parts of a project or even in different projects. And they also support extensibility, meaning we can easily extend existing code with new features without disrupting the entire system. Throughout this presentation, we'll see how these ideas come together to make software development more efficient, manageable, and scalable. Let's explore the differences between programming languages and programming paradigms. Programming languages are the tools we use to write software, like Python, Java, or C++. These are the actual syntax and commands that tell the computer what to do. Programming paradigms, on the other hand, are broader concepts or styles of programming, such as object-oriented or functional programming. They influence how we structure our code and solve problems. Next, we should differentiate between low-level and high-level programming languages. Low-level languages, like assembly or C, are closer to the hardware, giving us more control over hardware resources, but often requiring more detailed work. They can be faster and more efficient, but are harder to learn and use. High-level languages, like Python or JavaScript, are more abstracted from hardware, making them easier to write and understand. The trade-off is that they might be less efficient, but greatly improve developer productivity. Now let's look at 4 common programming paradigms. First, imperative programming, which focuses on how to perform tasks step by step. It's very straightforward but can lead to complex, hard-to-maintain code. Second, object-oriented programming, which organizes code into objects and classes, making it easier to manage large projects, though it can sometimes introduce unnecessary complexity. Third, functional programming emphasizes pure functions and immutability, leading to more predictable code but potentially a steeper learning curve. Finally, declarative programming, where you specify what you want without detailing how to do it, simplifies coding for certain tasks but may reduce control over the process. Understanding these paradigms helps us choose the right approach for different problems, aligning with our overall goal of writing efficient, maintainable software. So, what is a computer program? Well, the functions of a computer system are actually controlled by these programs. Think of a computer program as a set of instructions that tell the computer exactly what to do. It's important that these instructions are clear and precise, so that only one meaning can be derived from them. This clarity ensures the computer can follow the instructions without any confusion. Now, these instructions are written in what we call a programming language. Programming languages are special tools that help us communicate with the computer in a way it can understand. Different languages are used for different kinds of tasks, but the key idea is that they allow us to create these step-by-step instructions that make the computer perform specific functions. Ultimately, understanding how programs work and how they are written brings us closer to grasping how computers operate and how we can harness their power effectively. Let's take a closer look at the main categories of programming languages. First, we have machine languages. These are the most basic type of languages, consisting of binary code that the computer's hardware can directly understand. Next, there are assembly languages, which are slightly more human-readable but still closely tied to the hardware. Both machine languages and assembly languages are often called low-level languages because they operate very close to the hardware, giving programmers detailed control. Finally, we have high-level languages, which are more abstracted from the hardware and easier for humans to read and write. Understanding these categories helps us see how programming languages evolve to balance control and ease of use, which is essential as we develop more complex software systems. Now let's take a closer look at machine language. At its core, it's a sequence of zeros and ones, which we call binary code. This is the most fundamental way a computer communicates directly with the hardware. Each instruction is specific to the CPU, meaning that different processors have their own unique set of instructions. One of the biggest advantages of machine language is that it's extremely fast and efficient because it's executed directly by the hardware without any translation needed. This means programs can run very quickly, making it ideal for performance-critical applications. However, there are some downsides. Since the instructions are tailored to a specific CPU, machine language isn't portable. If you switch to a different type of processor, the code won't work without modification. Additionally, because it's just zeros and ones, it's very hard for humans to read or write directly, which makes programming in machine language complex and error-prone. So, while machine language is powerful, its limitations highlight why we often use higher-level languages for everyday programming. But understanding this foundation is key to grasping how computers operate at their most basic level. Now, let's talk about how mnemonics are used to represent machine instructions. Mnemonics are essentially symbolic names or short codes that we use in assembly language to stand for specific machine instructions. They serve as a human-readable way to write what would otherwise be long strings of binary code. Think of mnemonics as a one-to-one mapping with machine code, meaning each mnemonic directly corresponds to a specific machine instruction. This makes it easier for programmers to write and understand assembly programs without having to memorize all the binary patterns. However, it's important to remember that using mnemonics has both advantages and disadvantages. The benefits are quite similar to writing in machine language. They are fast and efficient because they directly translate to machine instructions. But on the downside, they are not portable across different types of processors, and they can be quite hard to read if you're not familiar with the specific mnemonics and what they represent. For example, look at this. The machine code might be something like 10-10-1, which is quite cryptic. In assembly language, this could be written as MOVX, var1, which is much more understandable. In summary, mnemonics strike a balance. They simplify programming at a low level, but also come with limitations in portability and readability. This is an essential part of understanding how assembly language bridges human readability and machine instructions. Let's talk about English-like statements and syntax. When writing high-level code, we want to use keywords that resemble English, such as if, while, and print. This makes the code more understandable and easier to follow. However, it's crucial to follow strict grammar rules or syntax to ensure the code works correctly. For example, writing if x0 print positive is correct, but if you try to write it as if x0 print positive, that would be incorrect because it doesn't follow proper syntax. High-level languages also come with built-in primitives like numbers, strings, and operators such as plus, minus, and multiply. These help us write more straightforward code without worrying about low-level details. Now, to run this code on a computer, we need a translator, either a compiler or an interpreter. That converts our high-level language into machine language that the computer can understand. Languages like C, C++, Java, Fortran, Visual Basic, Delphi, and Python are popular examples of high-level languages. There are some clear advantages to using high-level languages. They are portable, meaning the same code can run on different machines with minimal changes. They are also more programmer-friendly, making code easier to read, write, and debug. Of course, there are some disadvantages too. High-level languages tend to be less efficient. They run slower than low-level languages because of the extra translation step. Plus, they always require a compiler or interpreter to translate the code before execution. In summary, high-level languages help us write clearer, more portable code, but we need to be mindful of their efficiency and the translation process involved. A programming paradigm is essentially an approach or style we use to solve programming problems. It's like choosing the right toolbox for a specific task. Different programming languages are designed with particular paradigms in mind, which means they are optimized for certain kinds of applications and problem-solving strategies. Some of the most common paradigms you'll encounter include procedural programming, which focuses on a sequence of instructions, object-oriented programming, or OOP, which organizes code into objects that represent real-world entities, functional programming, where functions are treated as first-class citizens and emphasize immutability, and logic programming, which utilizes formal logic to make deductions and solve problems. Understanding these paradigms helps us choose the right language and approach for a given project. It also ties into the broader theme of how different tools and methods can be used to efficiently and effectively solve problems in programming. Let's talk about what a program really is. Essentially, it's a series of statements that change memory contents step by step. This means that when a program runs, it executes these instructions in sequence, modifying data along the way. You can see examples of programming languages that follow this approach, such as C, Fortran, Pascal, and COBOL. These languages are designed around this concept of step-by-step execution, which makes them straightforward to understand in terms of how a program manipulates data. One of the biggest advantages of this approach is efficiency. Because the instructions are executed directly and in order, programs tend to run quickly and use memory sparingly. This efficiency has made imperative or procedural programming widely adopted across many industries. However, there are some challenges. For instance, reasoning about complex programs can become quite difficult, especially as they grow in size and complexity. Tracking how data changes throughout the program isn't always straightforward. Additionally, parallelizing these programs, that is, running multiple parts simultaneously, can be tricky because of the dependencies between steps. Compared to modern programming paradigms, imperative or procedural programming is considered relatively low-level. It gives you fine-grained control over hardware and memory, but that also means you need to manage more details yourself. Overall, this paradigm is what we call imperative or procedural programming. It's all about giving instructions that change memory step by step, which has been a foundational approach in software development. OOP, or object-oriented programming, is a programming paradigm that uses the concept of objects to structure and organize code. It's based on core principles like abstraction, encapsulation, inheritance, and polymorphism. These principles help developers create software that is more flexible, reusable, and easier to maintain. The idea is to focus on modeling real-world entities, making it more intuitive to translate real-world problems into code. Languages like Java, C++, and C# are popular examples of OOP languages. One of the main advantages of OOP is that it's conceptually simple and intuitive once you understand the principles. It allows for better modeling of real-world problems and can significantly increase productivity. However, there are some challenges too. For beginners, the learning curve can be quite steep. Also, input and output operations can sometimes feel cumbersome in an object-oriented approach. Overall, OOP is a powerful way to think about programming, especially when dealing with complex systems that benefit from clear, modular design. Now, let's take a closer look at what defines a functional program. Essentially, a program in this paradigm is made up of functions that call each other, forming a kind of network of operations. What's interesting is that these functions don't rely on variables. Instead, they return results directly, which makes the flow more straightforward. Because of this, execution tends to feel more mathematical or formula-like, emphasizing clear, predictable transformations. Some common examples of functional languages include Haskell, ML, and Miranda. These languages are designed to support this style of programming, and they offer some notable advantages. For instance, their syntax tends to be very clean and concise, making the code easier to read and write. This clarity also helps developers reason about their programs more easily, since the logic flows in a transparent way. Additionally, functions are treated as first-class values, meaning they can be passed around and manipulated just like data. This opens up powerful programming techniques. Of course, there are some challenges too. Handling input and output can be more difficult because the pure functional approach doesn't naturally accommodate side effects or state changes. Also, functional programs often use more memory or storage compared to imperative languages, mainly due to the way they handle data and function calls. Overall, functional programming offers a different way of thinking about software design, focusing on pure functions and mathematical clarity, which can lead to very robust and maintainable code. But it also requires some adjustments in how we approach I/O and resource management. So, when we talk about a program, we're essentially referring to a set of predicates and rules of inference. Unlike traditional programming, which relies on step-by-step instructions, logic programming is based on formal logic. This means that instead of telling the computer exactly how to do something, we specify facts and rules, and the system figures out the solutions through logical reasoning. For example, Prolog, which stands for Programming in Logic, is a popular language in this paradigm. It's used to solve problems by defining facts, rules, and queries, allowing the system to infer new information. The key advantage here is that it supports logical reasoning, making solutions more concise and often easier to understand. However, there are some disadvantages to be aware of. Logic programs can be slow to execute because the system has to search through many possibilities. Also, since the program only knows what we've explicitly defined, facts and rules, its view of the world is limited. Debugging large logic programs can also be challenging, as it's not always straightforward to trace the reasoning steps. Overall, this approach emphasizes the power of logic and inference, which ties into the broader theme of understanding different programming paradigms and how they can be used to solve complex problems efficiently. Let's take a closer look at how structured or procedural programming compares to object-oriented programming, or OOP. In terms of focus, procedural programming emphasizes functions or procedures and the sequence in which they are executed. It's all about step-by-step instructions. On the other hand, OOP centers around objects, which contain data, called states, and behaviors, which are methods that operate on that data. When it comes to data handling, procedural programming often relies on global data or passing data explicitly to functions, which can be less secure and harder to manage as programs grow larger. Conversely, OOP encapsulates data within objects, promoting data hiding and controlled access, which enhances security and organization. The design approach is another key difference. Procedural programming tends to follow a top-down approach, breaking down problems into smaller functions. OOP, however, adopts a bottom-up strategy, building systems from interacting objects, which makes complex systems more manageable. Code reusability also varies significantly. Procedural code generally offers limited reusability, primarily through function calls. OOP excels here, enabling high reusability through classes and inheritance, allowing us to extend functionality without rewriting existing code. Regarding maintainability, procedural code can become quite complex to modify and maintain, especially in large projects, because of its linear structure. OOP simplifies this process because modularity and encapsulation make it easier to update or modify parts of the system independently. Finally, extensibility is much more straightforward in OOP. Adding new features by creating new classes or inheriting from existing ones usually involves less effort compared to procedural programming, where logic and data are often tightly intertwined and harder to extend. So overall, while procedural programming has its place, especially in simple tasks, OOP provides a more flexible, secure, and scalable approach for complex software development. There is no single best paradigm for all problems. That's an important point to remember as we explore different programming approaches. In practice, developers often use hybrid approaches, combining elements from various paradigms to solve complex issues more effectively. The choice of which paradigm to use really depends on several factors. First, the nature of the problem itself. Some problems are better suited to object-oriented methods, while others might benefit from functional programming. Second, the expertise of the team matters. What languages and paradigms they are comfortable with can influence the decision. And third, performance requirements. Certain paradigms can offer advantages in speed or resource management. As we continue our search for the ultimate programming language, it's clear that each paradigm has its own strengths and trade-offs. No single approach is perfect for every situation, and that's what makes this field so dynamic and interesting. Ultimately, understanding these differences helps us make better choices tailored to our specific project needs. Let's talk about abstraction. It's all about focusing on the essential features of an object while hiding the unnecessary details. This helps us reduce complexity, making our systems easier to understand and work with. For example, think of a car class. It might have start and drive methods, but it hides the complicated details of how the engine actually works inside. Now, moving on to encapsulation. This is about bundling data and the methods that operate on that data into a single unit, which we call a class. The main goal here is to protect our data from unauthorized access. For instance, imagine a bank account class with a private balance variable. You can only change the balance through specific methods like deposit and withdraw, which control how the data is modified. Next, we have information hiding. This means restricting direct access to certain parts of an object to improve security and reduce dependencies between different parts of our program. We do this using access modifiers like private, public, and protected. By controlling access in this way, we make our code more robust and easier to maintain. These concepts, abstraction, encapsulation, and information hiding, are fundamental to object-oriented programming. They help us build more secure, manageable, and understandable software systems. They're all about managing complexity and keeping our code organized and protected. Let's talk about reusability first. This is a really powerful concept in programming because it allows us to use existing code in multiple places, which helps us avoid duplication. When we design classes and methods thoughtfully, we can reuse them across different programs, saving time and effort. For example, imagine we have a vehicle class. Instead of rewriting code for each specific vehicle, we can reuse this vehicle class to create more specialized classes like car and bike. This approach makes our code more efficient and easier to maintain. Now, moving on to extensibility. This is all about adding new features without having to change the existing code, which is crucial for keeping our programs flexible and scalable. For instance, if we want to add an electric car class, we can do so by extending the vehicle class. This way, we introduce new functionality seamlessly without disrupting what we already have. Both reusability and extensibility are key aspects of good software design. They help us build systems that are not only efficient, but also adaptable to future needs, aligning perfectly with the overall goal of creating robust, maintainable code. Thank you so much for your attention today. I really appreciate your time and engagement. Now, I'd like to open the floor for any questions you might have. Please feel free to ask anything that's on your mind. Remember, this marks the end of Chapter 1, so we've covered some foundational concepts that will be important as we move forward. Thanks again for being here, and I look forward to our next session together.